That's the one. That's like,
I'm running out like all the work next week.
Yeah.
One day.
All right. There's one, guys, there's one type of problem that I want to go over with you. This was from Friday's homework. 2.2a practice AP problems. Number one, and I want to spend time going over this because it's very, very popular, common type of AP multiple choice questions. So I want to make sure that we're comfortable with this. I mean, obviously, we're going to see this over the course of the year once we get to AP review, but so everybody have this in front of them. So this is 2.2 AP practice problems. Number one here, I'm going to put this on a separate sheet so I can show the work. Okay, so we have a piecewise function. We're trying to solve for a and b. We know our function is differentiable. So what that means is that not only are these two branches of graph going to connect at 1, they're going to connect at 1. They're going to share the same y value at 1, but they're also going to share the same slope. So we are looking for a situation where these two graphs are going to connect nicely in a way where the graphs will have a smooth transition between the 2 points. That means they will share the same slope, so that will cause it to be differentiable, and they will share the same y value, which means that it will also be continuous. So it can't be a smooth curve unless it connects. And so that allows us to solve for a and b because we got to create two separate equations to allow for us to solve for two different values. So keep in mind that x is a variable, so x is a changing value, but a and b are constants. Okay, a and b are constants. So it says if f is differentiable at x equals 1, then a plus b is equal to. So here's the strategy that will allow us to create the information necessary to solve for a and b. So the first is we know that they're connected. Okay, so even though they don't say it, the understood knowledge here is that the function is also continuous, right? And that's kind of like a prerequisite, right? You can't have a differentiable function without being continuous. So I'm going to write that information out here. We know our function is continuous at x equals 1, which means that they must share the same y value at x equals 1, which means that we can set these two equal to each other and replace 1 for x, and that will create an equation that we know and want to be true. So we can say x squared minus ax equals ax plus b, right? We know that these two branches, they must share the same y value, so we can set them equal to each other at 1, so I can replace 1 in for all the x's. So if I combine some like terms here, I'll get 1 plus 2a equals, I'm sorry, 1 is equal to 2a plus b. We're still kind of stuck, right? There's still two unknown values, so we need some help from another equation that we're going to create. So the other equation that we can create is that our function is not only continuous, it's also differentiable. That's what they're telling us. At x equals 1. So what that means is that these two graphs, they must share the same slope. at x equals 1. So what that means is now we can not only set the functions equal to each other, we can set their what? Derivatives, right? Because we want these derivatives to share the same slope, so we can set their derivatives equal to each other. So let's create an f prime piecewise function. And remember, you're going to treat a like you would if it was a 3 or 4 or some unknown constant. So what's the derivative of x squared minus ax?
That's minus A.
Minus a, right? So imagine this was 3x, right? The derivative of 3x would be 3. So therefore, the derivative of ax would just be a. Ax plus b, what's ax plus b's derivative?
X.
A. Okay.
A plus 0, right? Imagine this was 3x plus 2. If it was 3x plus 2, you would simply say 3. So same thing here, ax plus b is just a. So sometimes I feel like some students make a mistake with the derivatives when there's constants, when these are a's and b's involved. So if you want to just double check yourself, pretend like a and b are just some numbers that you know and see if those line up, right? See if you're finding the derivatives the same way as you would if it was just a number like 5x plus 4. Okay. So now that I have my derivatives, I'm going to set them equal to each other. And I know what my x value is. What's my x value? At 1, right? Because we know that this behavior is occurring only at 1. They're only going to share the same slope at 1. So we can replace 1 in for x. So then we have something that works. A is 1. And if we can solve for A, now we can turn around and solve for B. So therefore, our answer is what's A plus B? A plus B is 1 minus 1, which is 0. So that's our answer there. Okay. Does that make sense for everyone? All right, so just know that this is a very popular type of AP multiple choice question that shows up a lot. So, and the reason why they like this problem is because they want to see, students understand what differentiable means and what that means for this piecewise function, right? That if they're going to connect at a smooth transition, they must also connect with the same y value and test students to see if they can see that relationship, build that relationship, and use these relationships to help solve for the missing information. So there's a lot, like they like these problems because it packs so much information and knowledge into one problem. So they like these types of problems. Okay. All right, let's go to our notes. Okay, so a little bit of review with natural log and exponential functions. Natural log and exponential functions are inverses of each other. So if I had, let's say this is my e to the x graph, and then my natural log graph. Exponential functions and natural log graphs will always have flipped order pairs. So there's an order pair that lives here. That flipped version of that order pair will live here. So an example of that would be if there's an order pair of 1, 0 that lives on natural log, which means that there's an order pair of 0, 1 that lives on e to the x. Right? They're inverses of each other. And because of that, we also have some interesting properties that we see here. Okay, first, and then also some properties within natural log and within exponential. Natural log of 1 is going to be 0. Natural log of 0 is undefined because natural log is never going to hit that x-axis. There's a vertical asymptote running along that y equals natural log x graph. So it's undefined. E to the 0 is equal to 1. Anything raised to the 0 power is 1. E to the natural log of A, E and natural log have a way of canceling each other out. So I'm just left with A if I do that. Likewise, if I have natural log of E to the A, that A can come down because that's a natural log property. And natural log of E is simply 1. So A times 1 is just A. So that's just to basically show that if I insert a natural log into exponential, or if I insert exponential into logs, they're going to cancel each other out because they're inverses. So we have derivatives of exponential functions and derivatives of log functions. Right now, we're just focused on base E. We're going to talk about other bases later, but these are the main ones. Okay, so e to the x's derivative is simply just e to the x. So that's nice. Exponential functions derivative is just the original expression. Natural log's derivative is 1 over x. And we have more to explore later on, but right now we're just doing the very basic of these rules. And then later on, when we introduce chain rule, then there's a little bit more that's involved, but at least we can kind of get used to these base rules here. Okay, so number 4, find the value of the derivative of the given points. So we're going to find each term's derivative. And once we find each term's derivative, we can insert 5 into its derivative function. So let's find f prime of x. 3 is a coefficient. It's just going to hang on in front. What's natural log of x's derivative? 1 over x. So it's just 3 times 1 over x, or you can just do it as 3 over x if you want to. What's e to the x's derivative? Just e to the x. That's nice, right? That's the exact same function as what you started with. All right, so there's my derivative. This is describing how the slope of this original graph is changing. So now we can find f prime of 5. So 3 times 1/5 plus e to the 5th. So 3/5 plus e to the 5th. So if I want to find out what is the slope of this graph at 5, whatever this number is, that's describing the steepness of this original graph. Okay. 5, asking pretty much the same thing. What is the slope of the tangent line to the graph at point x equals 8? Find the derivative, plug 8 into the derivative, and then get the slope. Okay, so try 5 and 6. Those should come pretty easy. Okay, any questions with 5? All right, number 6, same idea. Find the derivative of each term. And then once you have the derivative going, then plug 1 into the remaining derivative function. Now, I just want to point something out here. E is a irrational number around like 2.71. So what's the derivative of E?
0.
0. Good. So I want to keep that in mind, that e to the x is going to produce e to the x, but e's derivative is simply just 0. It's like a 3 or 5 or 6. Just go to 0. Okay, so 4 natural log of x becomes 4 times 1 over x. 3 e to the x is just 3 times e to the x. So basically any coefficient in front of a expression that's a variable in it, it'll just tag along. It'll just kind of hang on in front. It's not going to go away. Now, if a constant is by itself with no variable attached to it, then it will go to 0. But if a coefficient is attached to a variable, if you find the derivative, it will stay. It won't go away. Okay, next page. We're pretty good here. We're also going to talk a little bit about a brief introduction into trig derivatives. And then we'll discover a lot more towards the end of this unit after product rule and quotient rule tomorrow. Okay, so derivatives of cosine and sine. So the nice thing is that cosine and sine kind of describe each other's slope behavior. So that's a nice feature. With some exception here, cosine's derivative is going to be negative sine of x. So it's going to be the negative sine graph that's going to be describing the slope behavior of cosine. But sine's derivative is cosine of x. So cosine is going to do the job of describing the slope behavior of the sine curve. Okay, so here's the example here. Find f prime if f of x equals 2 sine of x minus 5 cosine of x. So f prime. The 2 is going to stay because it's hanging out in front of a variable expression. What's sine x's derivative? Cosine x. So simply make that replacement. Cosine's derivative is negative sine. So just be careful. We have to keep track of those double negatives there. So whatever this graph looks like, this derivative is going to do the job of telling us how the slope is changing at every moment, or what the slope value is at every x value. Okay, 13, if f of x equals 4e to the x plus 5 sine of x, find f prime of 0. Okay, try that. So 13, two-step process. Find f prime of x first, and then you can insert 0 to find a slope value. So 13, you're trying to get down to a numeric value. Right, 4e to the x stays as 4e to the x. 5 sine of x becomes 5 cosine of x. The nice thing is that since every term is separated by plus or minus, every term can be treated as its own thing, and we're just basically tackling different derivatives based off of what function we're dealing with, and then at the end we'll just piece them together with a plus or minus. So now that we have our derivative function, we can insert 0 for all the x's. Remember, anything raised to the 0 power is 1. So cosine of 0, that's a unit circle value. Cosine of 0 is 1. 4 plus 5 is 9. Try 14. Okay, let's check our answer. Okay, question with 13 or 14. Okay, I want you to try 15 and 16. Should be pretty straightforward. It says find the equation of the tangent line at the given x value. So gather your information, right? They give you the x, but you can find the y value using the original function. Get your ordered pair. Find the derivative. From the derivative, find the slope. Once you have your ordered pair in your slope, point slope form. Then also you may have to recall some of your unit circle values. Okay, check 15, see how you did. Oh, whoops, let's see. You're right. It should be pi over 2, comma. Pi over 2, pi over 2. Is that what you guys got? Both x and y are the same? Okay, thanks. Number 16. Right, we identify that there are 3 different rules at play for 16. You got e to the x, you got sine, you got power rule. Find each appropriate term's derivative. Then find the slope at 0. Find the order pair at 0. And point slope form. I went further. It was easy enough for me to solve for y, but you don't have to. You can leave your answer unsimplified point slope form, and if it's free response, you'll get full credit. So there's no. The only time you may have to clean this up is if there's multiple choice and you're trying to match your answer with something that is cleaned up in like slope intercept form or different form. Okay, any questions? Yeah, so I don't have a whole lot to go over. So this is it for notes. I'd like for you guys to use the rest of the time to see how much progress you can make with the homework. So more time for homework here, less time for you to do that work at home. So, okay, go ahead, start your homework. So what you can do is, you can set this equal to the slope here. So the slope is going to be -1. So I can use that to solve for x, right? Because this line has a slope of -1, and that slope is going to share with this slope. So I can set 1 equal to 2x minus 5 and solve for x.
But how do they have different slopes?
Well, let me put the answer up and then I'll walk you through it.
Okay, that's sure.
Okay, so the what I did for number 2 here is, well, I have 2 functions, right? And I can create a slope formula for both functions. For this one, you did f prime, which is fine, 2x minus 5, that's great. This also has a slope, right? What's the slope of this line? If I solve for y equals negative 1x plus k, right? So the slope is negative 5.
Yeah, but how would it have different slopes? So.
Well, this curve, it says, find the, so k is constant, tangent to the graph was valid case. So let's say we had this curve here. And then let's say the line is that is over here. So you're trying to figure out the k value that will allow these two to match and have the same slope. So
I got it mixed up as two functions, the way to slope.
yeah.
Yeah, I got understand.
Yeah, so we're working with two different things here, so we know that, okay, if they're gonna share the same slope, then because this slope is -1, that means the curve must have a slope of -1 here. And if I have a slope of -1, I can solve for x,
Plug it in.
x is 2, and once I have the value for 2, I can solve for k.
I understand. Good. I got you.
Alright, 这样子。
Number 11. That's a sharp turn.
So I set half prime this, and then see sometimes be a. So. Why can't they just say that?
That's one thing.
Usually interesting. Yeah, okay, I think you can then look at that intersection. That intersection, you can X out. See, I didn't also know what's next. There was a
Solutions.
Yeah. So I think, okay, so I should have set that equal to 0. Found the x-intercept. And then the y will have must be equal. So let me try that. 2x cubed.
It's a perfect.
But that's it. So
And negative.
yeah. Oh, it's never mind. Yeah.
I mean, that's how it's gonna be. It goes back. Yeah.
I get it. 20.
Well, there is some, but I think you have.
Okay.
She makes a lot of sense. Yeah. I think it's just not working.
Right.
I'm gonna take it out.
So now you pick the version of
What I
that.
got to understand is that I'm not doing this with global.
Yeah.
Yeah.
So you go to one.
Yeah, that was like how.
Oh, and then that, five, that. Back into the.
Today was like that. I mean, rock out.
Good work.
Yeah.
It's never less than You see is all real numbers.
I don't know, what does the zero put next to that? Inflation prime X are on top.
That tells you the slope. That's the slope that you want the equation to be.
Except
So
the
this
velocity.
is right, the equation of tangent line. So tangent line just means
The
we're here.
velocity. That's true. Both really like that. Wait, do I just send this equal to zero and set the limit? Wait, I thought it gets more advanced. Is it that easy? It's like a simple. I mean, shut up. Wait, it's really on three? I just said it's six days. Then you should even. $39, yeah. And then I'll backwards.
Okay, correct on 35. Okay, working for this one.
I got it. Negative X plus.
I forgot to change the negative.
Okay, sorry. So what I should have done, once I got this point, I should have turned into the original function to get the y value.
The question is velocity. Wait, oh, this is position. So velocity.
Yeah.
Oh, that is.
Yeah.
Oh.
That's like. It's like. No, I mean,
Oh, this is really easy. Yes, right, I know it's true. Yeah.
And I think, fine, so.
I need to know how to
All of them made a line.
It's the natural log of. Yeah, that's probably.
Lady going to do that.
But. Yes.
You can also sit back to.
There's no test. Yeah, but it's still pretty. Yeah. That phone takes up.